Let me show you in this video how to deal with the directionality in crossed fields problems, okay? And this might be the first video you're seeing on crossed fields, so let me just explain the basic concept. Let's pick a polarity of a charge, like a positive charge. This could be a proton, right? And this is actually a really cool thing, right? We can send this positive particle into the space between these plates where we're generating an electric field up the page. The bottom plate's charged positively. The top plate is charged negatively, okay? We send it in here. Well, clearly there's going to be an electric force this way. But if we're clever about this, we can have a magnetic field exert a magnetic force that counteracts that. And this allows the particle to go straight. And this is important for a number of reasons that I'll explain here in a second, okay? So first off, what you have for this is you've got a given field here, right? The given field is the electric field. It's up the page. So the first step is to figure out the direction that the given field exerts on the particle that you have. And in this case, it's a positive particle. The electric field's simply going to exert a force up because that's what upward electric fields do with positive particles, okay? Now to counteract it, we would have to have a magnetic field that's down the page. For it to go straight, these guys would have to be equal. Now mathematically, this means that our electric force, which is EQ, is going to be counteracted or equal to, but opposite, right? The magnetic force, which is QVB. Notice that the charge cancels. This is super important and kind of cool. As long as it has charge, it can't be zero. In other words, we can't divide by zero. It can't be an uncharged particle. This won't work with neutrons, in other words, okay? Or neutral pions or whatever you have, right? Okay, it's only going to work with particles that actually have a charge, a non-zero charge, right? And the charge will cancel like this. Now, let's just go. I'm getting ahead of myself here. So now the question is, what direction does the magnetic field have to be to counteract this upward electric force? Well, it's got to exert a downward force. So that's our thumb in that calculation, right? So put your thumb that way, put your index finger this way. Okay, so I've got my index finger to the right, I've got my thumb down the page, and after some contortions, I've got my middle finger pointing out of the page, okay? Okay. Now, if you make the magnetic field equal to the electric field divided by the velocity, okay, then if you tune it just right, make the magnetic field exactly that, this particle will go straight. Isn't that fun? Now, what you can do is you can make a little like a pinhole camera here, a little hole right there, okay, and you can have particles come in here. And if they have exactly the right velocity, see the magnetic field and the electric field, you just keep constant. If they have exactly the right velocity, then they can go straight across, okay? If they're going a little bit faster, they're going to deflect downward because the magnetic force actually, it depends on the velocity, right? So if you double the velocity, you get more magnetic force. And since the magnetic force is down, faster particles will curve this way, right? If it's faster than whatever that velocity is that you calculated, whatever you used for this, right? Slower particles are going to have less magnetic force, so slower particles will deflect this way. And this is a way that you can either determine whether it's faster or slower than a certain velocity, right? Okay, now the slower is going to deflect this way because if it's going slower than the velocity you calculated these two fields for, right, then the magnetic force is actually going to be less. And so therefore the electric force will be stronger and it's going to deflect upward, okay? But if it's got the same velocity and you put a hole, it's straight across like that, only the ones with that particular velocity can get through this little cross fields region. So it becomes a way to select particles that have a particular velocity. And we use this for mass spectrometers and other things that, that I'd have to go to more school to learn about. But anyway, now let's look at the situation. So remember that we predicted a magnetic field out of the page, okay? What if that were a negative particle? What if it were an electron, okay? Let's go ahead and do the same prediction of the direction for an electron. Okay, I'm about to erase this. Are you ready for this? Boom. Now it's a negative particle, okay? Well, we're going to do the same thing, okay? So the electric field is up the page. If the electric field is up the page, that means the electric force is actually down the page on an electron because it's negative, right? The force is EQ, right? So whatever that is up the page times a negative charge makes it down the page, or negative up the page, right? Okay, so our electric force is down the page. So now the question is, which direction is the magnetic field so that it exerts a force up the page on this particle, okay? Now, remember, it's a little bit tricky, but not too tricky, right? So let's go index finger this way, thumb this way. Remember that we're going to predict a direction of the field, but then reverse it because it's a negative charge, right? Okay, so index finger to the right and thumb up this page, right? Index finger to the right. I can do this without contortion. This is good. So my index finger is to the right, my thumb is up the page, and my middle finger is pointing into the page. My middle finger is into the page. So remember that the magnetic field is negative into the page, so therefore the magnetic field is out of the page. Now that's complicated, right? First we had to reverse the electric force, then we had to reverse the electric magnetic field that we predicted because it's a negative particle, and negative particles have a negative in their magnitude, and it reverses all these forces. Now, the moral of this story is, boy, isn't it easier to predict positive charges? And don't positive charges lead to the same prediction? Don't they? Yeah, I think they do, right? Okay. Now, let's think about this, right? What if we speed this particle up? Because we've got these two forces. We've got the electric force, which is EQ. We've got the magnetic force, which is QVB. So here's what I'm saying. Let's imagine that we tune this up, that we make our electric field equal to the velocity times v, right? Because if you set these equal, right, the q's cancel out. So electric field equals vb. Let's tune this up so that it picks a particular velocity. Now, what if we speed this up? If we speed this guy up, which force is going to get bigger? Well, this one doesn't depend on velocity. This one does. Okay? So if I speed this guy up, remember that, so if I speed this up, it's going to actually deflect this way. A particle that's faster is actually going to deflect this way, and that's because the magnetic force, which is up the page here, is going to get bigger. It's going to get bigger because it depends on the velocity. Okay? If a particle is going slower, well, then if we set these guys equal, right, the EQ equal the QVB, well, if it's going slower, well, now suddenly this guy's bigger, right? Okay, the EQ is going to be bigger, and therefore it's going to, okay? And those predictions are the opposite, okay? But as far as the direction of the magnetic field to affect a straight across path, that is not affected by the polarity of the charge.